Okay, let us start with the talk. But first, I want to thank the organizers, especially Leandro for the introduction that he gave. This outstanding mathematician is too much for me. I'm sorry, but I'm a normal mathematician at least. Okay, let me begin with the talk and thank the organizers for the whole organization of this meeting. The talk is about convex functions and convexity and the relation between convexity and eigenvalues of the Hessian, and is based on joint works with Pablo Blanc, who is now in Finland, Carlos Esteve, who is now at Autónoma in Madrid, and Leandro del Peso from Buenos Aires, and Nicolás Frevenza from Montevideo, Uruguay. Okay, let us start with the simplest stuff. In Rn, if you have a domain omega in Rn and a function u inside omega, u is said to be convex if the value of the function at a convex combination between 2 points is less or equal than the convex combination between the values at the extreme points. That is to say that the graph of u inside the segment that joins x and y is less or equal than the straight line that joins u of x and u of y. Okay, now given a boundary data, f, a function defined on the boundary, you can try to look for the convex envelope of this boundary data inside the domain, inside omega, and this boundary, this convex envelope of the boundary data is given by this u star. U star is the supremum of all convex functions that are below f on the boundary and are convex inside omega of the values of u of x. So you take the largest possible convex function that is below f on the boundary of your set, and this is your convex envelope of the function. Okay, in terms of the eigenvalues of the Hessian, what do you have? A function that is C2, that is smooth, is convex. Then the matrix, the Hessian, has to be positive semi-definite. So the second derivative in any direction of your function u has to be bigger or equal than 0. And this is because if you have a negative second derivative in one direction, then your function fails to be convex. It is concave in one direction, at least locally near the point there. So this condition that the second derivatives of u times v, this is equivalent to convexity. So in terms of the eigenvalues, if you compute the infimum of all these products of the matrix of the Hessian times v, this is the minimum of the eigenvalues, the smallest eigenvalue of your Hessian. And this I will call it lambda 1 of d2u. And this lambda 1 of d2u has to be bigger or equal than 0 for a convex function. And it turns out that this is equivalent to convexity if this inequality lambda 1 bigger or equal than 0 is understood in the viscosity sense, in a viscosity sense. Okay, concerning the convex envelope, then when you take the supremum of all convex functions that are below f on the boundary, then your convex envelope is a solution to the equation. It's lambda 1 of d2u equals to 0, so you saturate the constraint, because if at some point you have that lambda 1 is strictly positive, you have room for going up a little more. Okay, for other eigenvalues, not only for lambda 1, you have this formula. This formula comes from linear algebra, elementary linear algebra. You take your matrix, your n times n matrix symmetric, you multiply by v times v, and you compute then the infimum among subspaces of dimension j, and the supremum among vectors in the subspace. And this inf sup gives you the j eigenvalue if you order the eigenvalues. Okay, what is known is that there is a unique viscosity solution to lambda 1 with boundary data equals to f if the domain is convex and the function is continuous. And when you go one step further and compute for lambda j is the jth eigenvalue of the Hessian if you order them. The smallest one is lambda 1, The largest one, I call it lambda n, and lambda j should be something in between. Then for a strictly convex domain, and F continuous, there is also a unique viscosity solutions, and the condition on omega could be relaxed a little bit, well, not a little bit, it can be relaxed, but I will stick to strictly convex domain, not to enter into too many details. One question that I will, I don't know how to solve is the regularity issue. For lambda 1, it is known that if the boundary data is C1 alpha, then the solution is C1 alpha inside. For lambda j, for the j eigenvalue, this is not known. I don't know how to prove regularity of the solution inside from regularity in the boundary. What we can prove with Pablo Blanc is that solutions are Lipschitz continuous or has some modulus of continuity inside, but it is not clear how to show that the gradient has some modulus of continuity. So C1 alpha, I don't know how to do, and I would love to do it. Okay, about the evolution problem. Let me start talking about the evolution problem. The evolution problem associated with the eigenvalues of the Hessian is this one. So you take your elliptic equation, lambda j of d2u, and you add some ut in front. This is the evolution equation associated with this operator that is given in terms of the eigenvalues of the Hessian. Dirichlet boundary condition on the boundary of omega and an initial condition inside omega. And this problem is just the parabolic version of what you see previously. And what we have with Pablo Blanc and Carlos Esteve is the following theorem that says that you have an existence and uniqueness of a continuous solution up to the boundary, provided your boundary data F is compatible with the initial condition. So you need that the initial condition on the boundary is equal to F, to your boundary data F. This is just to have continuity up to the boundary and up to the initial condition. And at time t equals 0, and concerning the asymptotic behavior, which is I think the most interesting part of what we have done, we have exponential conversions in general. Solutions as t goes to infinity will go exponentially fast to the unique solution of the stationary problem, of the elliptic equation, associated elliptic equation. Okay, something extra is that when j, something extra and a little surprising for me at least, is that when j with the eigenvalue is not lambda 1 and not lambda n, then the evolution problem attains the stationary case, stationary solution. If you take boundary data equals to 0, the stationary solution is 0, is identically 0, but it is attained in finite time. So there exists a finite capital T depending only on omega, not in the initial condition of your evolution problem. So it depends only on the domain in such a way that when you run this evolution, it varies identically everywhere instantaneously. This expansion that we have in general is much better when you face let me say 0 boundary conditions, or when you face this affine boundary conditions. And we have two proofs of this result, of this asymptotic behavior and this reaching 0 in finite time. The first one is a pure PDE proof using sub and super solutions. And the second one, in fact, the order was exactly the reverse. We first find this game theory proof using a probabilistic interpretation, which I didn't mention, of these problems, of this elliptic and parabolic counterpart. But we found this game theory, approximation of the solutions to the parabolic problem. And in this game theory approximation, you can find a very nice argument that bounds the time in which your solution reaches 0. Okay, now I want to switch the problem to equations defined on the tree. On a regular tree, directed tree, what is this monster? We are going to try to understand convexity and quasi-convexity that I will define later in terms of a non-Euclidean setting. That is a graph. This is this tree graph. What is a tree? A tree is one root, one common ancestor to everyone, and each one, its root has 3 descendants. So each node, for each node of the graph, you have 3 kids, and I will name the kids 0, 1, and 2. 0 is in the left, 1 in the middle, and 2 on the right. And you continue, and so on and so on. So this is an infinite graph. So for example, this one is the node that corresponds to from the father going down in the center and then going left. This one is going left first and then go to the center and then go right, for example. This is the original node, the father of everyone. And you have a father, father, father. Every generation has only and exactly 3 kids. In this, of course, you can have m kids, and this is the m tree, regular tree. So this is a graph with a lot of structure, a lot of regularity inside, but this is an infinite graph. And things becomes nice to see how this convexity stuff carries on to this non-Euclidean setting. And of course, since you're here to see PDEs, there should be a PDE. There should be it's not going to be a PDE, but the analogous to a PDE in this setting, in this tree. So this is the ambient space in which we are going to define convexity, to try to look for convex functions. Okay, what is a branch? Now I'm going to talk about the boundary of the tree because I want to do the same thing. I want to pose a boundary data, define convexity, and then look for the convex envelope. So what is the boundary of the tree? The boundary of the tree is the following thing. A branch of the tree is an infinite collection of nodes starting from the father of all the points. So this going down, going left, going right, and continue. An infinite collection of numbers 0, 1, and 2 is a branch of the tree. And associated with this branch of the tree, I can provide a number in the interval between 0 and 1, just taking the expansion in basis 3. For example, if we are talking about the ternary tree, you take the number that begins with 0, 1, 0, 2, 2, 1, etc. And this provides you a number in the interval between 0 and 1. And of course, you have branches that gives you the same number, that are the branches that has, let me say, 2, 2, 2, 2, 2, 2, 2, 2, 2 at the end, or 0, 0, 0, 0, 0, 0 at the end. You have 2 branches, 2 periodic branches that give you the same number, but those branches has measures 0, so you don't care about them. In general, this is a nice function between what we call the boundary of the tree and the interval 0, 1. So we will identify the boundary of this object, of this regular tree with m branching as the interval 0, 1. So each branch, each infinite branch has attached to a number between 0 and 1. Okay, if you do that, if you have an object, an ambient space and its boundary, then you want to define what is a convex function. And to define what is a convex function, I need to introduce some extra thing, that is what is a segment. Because recall that a convex function in the Euclidean case, in the Euclidean space, is a function that whose graph is below the line, the straight line, between the endpoints of the segment inside the segment. So I need to see what is a segment inside the tree. And we will understand a segment inside the tree for the directed tree as a binary subgraph. And what is a binary subgraph? You choose one node, you choose this X here. And when you start with this X there, then you take 2 successors. Out of the 3 of them, you choose 2 of them. And in these 2, you choose 2 more. And this is these green dots are the nodes associated with one of these binary graphs with the root at X. So this is the first one, the first node that appears there. And you have 3 endpoints. The first endpoint is x, 1. So this is the first endpoint, and those two are the 2 second endpoints. So a binary subgraph inside the graph is you choose one node, and for each node you choose 2 successors, 2 successors, 2 successors, and so on. In a finite, you want to do it in a finite way, and this is going to be a segment. We will call the endpoints of this binary subgraph the extreme point of the segment, and this x is going to be the middle, the midpoint of the segment, the middle of the segment. So your definition of convexity, what is a function that is convex inside the tree, is the following thing. It's a function whose graph at the middle point of the segment is less or equal than the mean value of the function at the extreme points of the segment, at the extreme of the segment. In the Euclidean case, you only have 2 points as extreme points of the segment, and the midpoint inside says that u of 1/2 x plus 1/2 y is less or equal than 1/2 u of y plus 1/2 u of x. Here you have several extreme points, as I depicted in this picture, in which you have 1, 2, 3 extreme points. This one has weight 1/2, and these two has weight 1/4 and 1/4 each. And you are saying that the value of the function here at this node is less or equal than 1/2 the value here, plus 1/4 here, plus 1/4 here. So one easy remark is that the sum of these coefficients sum up to 1 in every binary tree. And this set E of B is the set of extreme points of the binary tree, and X is just the root. So what we are saying here is the definition of convexity is the same definition as convexity for the Euclidean case, except that in the tree we are understanding what is a segment in terms of these binary trees inside the ambient space. Okay, once we have this property of convexity, we can define what is the convex envelope of a function. If you have a function, capital F, defined on the boundary of the tree, so in the interval 0, 1, then you can compute the set of all possible binary convex functions defined inside the tree, for which the lim sup, as you go down in the branch, is less or equal than the function f, and you compute the supremum of all these possible convex functions that are below your boundary data when you approach the boundary, and this is your convex envelope of your function inside the tree. Okay, the convex envelope in the tree verifies an equation. Yeah, good. This is the analogous of lambda 1 equals to 0 for the Euclidean case. And this is a result with Leandro Del Peso and Nico Frevenza that says that the binary convex functions, the binary convex envelope, is a solution to this equation. So u of x is exactly the minimum taking 2 successors. This is the set of successors of x. So 2 nodes going down of the mean value between the two, u of y plus u of z over 2. And this is saying that in some sense you can characterize convexity in terms of a local equation that says from this x, you choose 2 of them, the 0, 1, and 2, two of the 3, and you take the mean between these. And if u of x verifies this equation, then it's going to be convex, and the convex envelope is going to be a solution to this thing. And there exists a unique, given a continuous boundary data f, there exists a unique function that is a solution to the equation, and the limit, the exact limit, is given by f. So you may say the Dirichlet boundary data for the analogous of the first eigenvalue of lambda 1 equals to 0 inside the tree has a unique solution, and this unique solution is exactly the convex envelope of your boundary data F. Okay, what is this equation in terms of the eigenvalues of the Hessian? Because here we don't have derivatives, we only have differences between things. But we want to understand this equation in terms of the eigenvalues of the Hessian. What is the analogous of the eigenvalues of the Hessian inside the tree? Okay, this one should be the equation corresponding to lambda 1 equals to 0. So you rewrite the equation in this form. You subtract u of x and you put inside the minimum. And these quantities are like the eigenvalues of the Hessian, and you're computing the minimum of all them. So this is a smaller eigenvalues of the Hessian. So the eigenvalues of the Hessian associated with this tree are the following things: are the mean value of two successors minus u at the father of the two successors, and all possible combinations between those two different sons of the father gives you all possible eigenvalues of the Hessian. And if you sum them, if you add up the eigenvalues of the Hessian, what you obtain is the Laplacian. This is in the Euclidean case. The Laplacian is the sum of the eigenvalues of the Hessian. In this binary tree, or in these trees, what you get is this equation. This equation says that the mean value of u in all the successors, in all the nodes that are below x, one level below x, minus the value of the function at the father is going to be 0. This is the Laplace equation. This is the Laplacian equals to 0 in the directed tree. This is the usual thing that was studied before for let me say, the tree. Or in any graph, if you want to look at the Laplacian, you ask a function to have values in such a way that the value at some node is equal to the mean value in the neighbors, and in the nodes that are connected with this node. This is the mean value property for harmonic functions, and this is what we try to reproduce. And this is exactly what you have here. It is a directed tree in the sense that you can only go down. So every node is connected with nodes that are below this node, and this is saying that the father can talk to the sons, but the sons cannot talk to the father again. Okay, this is the convex envelope of a function. Now I'm going to switch to a quasi-convex envelope. In Rn, in the Euclidean setting, what is a quasi-convex function? A quasi-convex function is the following: is a sort of convexity, but it's not convex in general. It's the following thing: it's a function u such that the function inside the segment, here you have the function u inside the segment that joins x and y, is less or equal than the maximum of the two endpoints. And why quasi-convex functions are interesting? This is a sort of generalization of convexity. If a function is convex, then it is quasi-convex. This is okay, because if the value inside the segment is less or equal than the convex combination between u of x and u of y, the convex combination between u of x and u of y is less or equal than the maximum of the 2 points, of the two extrema. And quasi-convex functions are nice because they have the same property as convex functions, in the sense that when you have a quasi-convex function that is inside the domain and is bounded and has some condition, let me say if the domain is infinity, you have some condition at infinity, then the function attains a minimum. And this is also true for quasi-convex functions. And if you have a strict inequality here, so if the inequality is strict, you have a strict quasi-convexity, then you have a unique minimum. And this is quite useful for applications, of course, and quasi-convex functions appears in economics and things like that. I don't know anything about the application. Let me say that I become more and more a pure mathematician when time evolves. But this this idea, try to generalize a little bit, is more general than convexity and has the same property of attaining minima that you want for a convex or quasi-convex function in general. This is what they are used for. Okay, this definition can be rephrased in terms of the level sets of the function, which is a nice stuff, and says that, okay, a function is quasi-convex if and only if the sublevel set, so you take the set of points in which u of x is less or equal than alpha, this sublevel set should be a convex set inside Rn. So if your function is defined in Rn, you take the sublevel set of the function, this is a subset of Rn, and you ask this to be convex. And now we want to generalize or to do this, to extend this definition to the tree and see what happens and see what is the equation associated with this quasi-convexity. Okay, for this, what we need is to do the extension to the tree. What we need is the idea of what is a segment inside the tree that we have. This is these binary subtrees. But we need to look at what is a convex set, because we are going to try to extend the definition with this idea, and says, okay, I will take the sublevel set. This will be a set of nodes. I want to say what is a convex set inside the tree. And a convex set inside the tree is the following. You take one of these binary subtrees. Now I'm going to let it to be a k-binary. That is, instead of only 2 successors, we are choosing k successors. But it's the same thing as binary. If you want to take k equals 2 and everything works the same thing. And you are saying that a set inside the tree is convex if every time you have the endpoints of one of these trees inside your set, then the root is in the set. So the definition of what is a convex subset of the tree says that Z is convex inside the tree if for every of these subtrees that you can build with the extreme points of the subtree inside your set C, then the root also has to belong to C. So if you go down with, let me say, 2 branches with this binary subtree, and you have that the extreme points are inside your set C, then the root, the first one, also have to be inside C. And this is notion of convexity of what is a convex set inside the tree. Okay, now the definition, the natural definition for being quasi-convex inside the tree is saying that these sets are convex inside the tree. The sublevel sets are convex. Okay, for this thing we have an equation, and the equation says the following: a function, any function, is quasi-convex inside the tree if and only if u of x is less or equal than the minimum between choosing k successors of the maximum of the function in these k successors. And this is more or less as saying that u of x is less or equal than the maximum at the extreme points for every possible segment that starts at u of x. Okay, and given a function, given a boundary data f, exactly as before, you have a unique quasi-convex envelope, and the unique quasi-convex envelope is a solution to the equation with equality here. So you have that u of x is this min-max of the values of u at the successors, and this equation, for this equation with the boundary data f, you have a unique solution, provided the boundary data is continuous. I didn't mention here, but the boundary data has to be continuous in order to have the limit up to the point. So you obtain the boundary data with continuity here. Okay, what is this equation? This equation that we saw before, this min-max, you can saw it in this way. if you have the chance that the number of nodes of each successor, let's say is 3, for example, in the ternary 3, and you take k equals to 2, then it is the median value. Instead of the mean for the Laplacian, you are computing the median, so the value that is the intermediate value between the values of u at the successors. And this equation, u of x equal the median of u at the successors, is exactly the equation that characterizes the quasi-convex envelope of a function. Okay, in terms of the parallel that we made with the equations in the Euclidean setting, what is the second derivative? A pure second derivative is going to be for us the difference between u of y minus u of x for some successors of y, a successor of x. So you are taking a direction is one direction to go down, and you're computing the difference between these two nodes going down. And if you add among all these possible second derivatives, so you add among all possible successors, you add in y, then you will find again this Laplacian, because you will have the sum of the successors minus n times the value at the point, so you will have a multiple, if you want, of the usual Laplacian. And in this sense, with this pure second derivatives, or with this analogous to the pure second derivatives, you are computing the Laplacian not as the sum of the eigenvalues of the Hessian, but as the sum of the pure second derivatives. And it's the same operator at the end. Okay, if you want to identify the direction of the gradient of a function, inside the tree, you want to look for the infinity Laplacian. What is the infinity Laplacian in the Euclidean case? The infinity Laplacian in the Euclidean case is given by the second derivative of the function in the direction of the gradient. And in the case of a tree, of a directed tree, the infinity Laplacian that was studied by Sviridov, Manfredi, and Overman is this monster that says that at a point, u of x is 1/2 the maximum of u at the successors plus 1/2 the minimum of u at the successors. This is the analogous to the infinity Laplacian. So what is the direction of the gradient? The direction of the gradient, you have two directions. The directions in which the function grows faster, and the direction in which the direction of the function grows slower. It's rapidly decreasing or rapidly increasing in one direction or in another direction. So the two directions are the two nodes, the two successors, the 2 points y, at which the maximum and the minimum of the function is attained. Now, if you compute for the Euclidean case, what is the equation that is satisfied by the quasi-convex envelope, or that characterizes the quasi-convex envelope, is this curious equation that holds in the viscosity sense. So you take at every point, you compute the Hessian, you compute the gradient of the function, if the function is smooth, and then you compute for vectors that are orthogonal to the gradient. So for directions orthogonal to the directions of the gradient, you compute the second derivatives. So you take a function, you compute the direction of the gradient in the orthogonal directions, you compute all possible second derivatives. And what you are saying is that the minimum of all possible second derivatives in the directions orthogonal to the gradient is going to be equal to 0. This is something related to quasi-convexity. And this is a result of Barron, Jensen, and somebody else that I don't remember. Sorry about that. Okay, now for the tree, you can do the same thing. And you can say, okay, I will take the two directions in which the maximum and the minimum of the successors is attained, and those are the directions of the gradient, and you compute the minimum among any other possible direction, any other possible successors that it is not the maximum and it is not the minimum of the second derivative, the pure second derivative in that direction. And if you do that, what you obtain is this thing. You obtain the U2, the second value of U in the ternary tree, the median of U minus U, which is exactly the equation that you have before and that characterizes the quasi-convex envelope of your function inside the tree. So also in this case, also for this ambient space and with this definition of quasi-convexity, what you have is a parallel between the equation that holds for quasi-convex functions in the Euclidean case and the equation that characterizes the quasi-convex envelope, which is this one with the median in this tree, in this let me say directed graph, infinite directed graph with a lot of regular graph. Okay, as a bunch of references. In these references, I want to mention this Obermann and Silvestre. This paper characterizes what is the convex envelope and deals with the regularity for the equation lambda 1 of d2u equals to 0. The papers by Sviridov and Manfredi, Obermann and Sviridov. Sviridov was a student of Manfredi, in fact, at Pittsburgh University, deals with this infinity Laplacian and also with the P Laplacian inside a graph, inside these trees. And we did something, this last reference with Del Peso, Frevenza, and myself is the reference associated with this convex extension. The reference for the quasi-convex extension, we are writing down the details. Let me say. Okay, this is what I want to say. I want to thank you very much for your attention, and I want to thank again the organizers for giving me the opportunity to give this talk and for the whole organization of this meeting. It's a sort of strange to give a talk in front of an audience that you don't see inside my kitchen, in fact, because I am at my kitchen in my place, having a coffee, comfortably sitting at my place. But I would like to travel again, and I would love to see you in person and have a coffee at the coffee break, and later on to have a beer at some bar and to collect anecdotes of about how crazy it was when that night we go out dancing until 3 o'clock in the morning, and next day at the first talk we were there. So thanks a lot for your attention.
Thank you, Julio, for your nice one.
Okay,
question?
It was just on time, no? 40 minutes?
Yes, perfect, perfect.
Oh.
Some comment?
Sorry,
question?
I have a question, please.
Yeah.
Sure, please.
Sorry, I turn on my video. I am Luciano Mari. I would like to talk to ask about the result with Blanc on the elliptic case.
Yeah.
Whether you have a modulus of continuity estimate also for the sum of the first J eigenvalues. If there is an interpretation.
Let me go again to the slides. Where are they? Here.
Exactly.
Okay, for the sum of the first J eigenvalues, there are results by Birindelli, Gallisi, and Ishii, and recent results by Birindelli, Gallisi, and Top. Okay. Also, but I don't know how to prove regularity of this equation in general.
Yeah, and I know just of the result with Ishii, but they deal with the lambda 1. Again,
no,
more general equation involving lambda 1.
Yeah, but only for lambda 1, this is known. For lambda 1 of d2u equals to 0 with the C1 alpha boundary data, this is the result by Obermann and Silvestre.
Exactly.
And the point here is that when you're talking about lambda 1, you are talking about the convex envelope. And for a convex function, you have something that is very useful, that is a supporting hyperplane at every point.
Exactly.
So you can touch your function from below at a point with a plane, with something that is linear.
Exactly.
And okay, you have to work a lot because it is not that simple to touch the function below at every point. With a plane, is not give you automatically regularity because you have a cone, for example, which is a convex function, and you don't have regularity C1 alpha at the vertex of the cone. But we're using the equation and using this idea of the supporting hyperplane, you can prove C1 alpha regularity. For lambda j equals to 0, I don't have any idea of what should be a supporting hyperplane for this equation, for this monster, for this
kind of a supporting j-dimensional space or something like this.
Maybe, but I don't know. I don't know how to prove that there such a thing exists, and I don't know how to use it to prove regularity. Both things I don't know. So,
okay.
And for the sum of the first j eigenvalues, I don't know either. But I never thought about this, the regularity problem for the sum, or let me say the first two eigenvalues of the Hessian. I didn't thought about this.
Well, actually, I was thinking just of a modulus of continuity estimate.
The modulus of continuity estimate for lambda j of d2u equals to 0, this can be proved using the game. The game theoretical interpretation that we have with Pablo Blanc gives you some modulus of continuity inside, if provided that the boundary data is smooth.
Okay, and you think that a game theoretical representation could be feasible also for the sum of the first j eigenvalues, or it's very specific to the single eigenvalue?
I think that it could be done for the sum of the first j eigenvalues. The game theoretical interpretation runs as follows. You have two players. The first player chooses a subspace of dimension j, and the other player chooses a vector inside the subspace. And then you go one step in the direction of this vector, or one step in the minus the direction of this vector with probability 1/2, 1/2.
Okay.
And you continue playing like this, choosing a subspace and a vector inside until you get out of the domain. And when you get out of the domain, player one pays to player two the amount of money given by f of x. F is the boundary data.
I got it.
For the sum of the first j eigenvalues, what you have to do is choose a subspace, and then inside the subspace, you choose an orthonormal basis, or you choose a ball inside this subspace, or you take and you move at random inside the ball. And this should give you, when you minimize or in the subspaces that you are choosing, this should give you the sum of the first j eigenvalues. And for that, you have to prove a uniform modulus of continuity. Maybe it can be done. Yeah.
Okay. Many thanks.
I didn't make the computations, but my guess, if you want to play to put money in there, I will put, let me say, 10 euros. It can be done, but okay. Not more than 10 euros, of course.
Okay, it's already
not 100. Yeah, not 100,
but thank you very much.
No, please, come on.
Sorry, I didn't hear very well.
No, on the contrary, thank you for the question, and write me an email whenever you want.
Great, thank you. Okay.
Please.
Okay, another question.
I have a question here, Erwin.
Sure. ¿Sí?
Julio, un abrazo, Julio.
Igualmente.
También te extraño mucho. Just a question and just a comment. What I've been working with Isabel and Julio is not related with the regularity, first thing. And the second question, the question is that you said that the modulus of continuity you get is Lipschitz regularity or not? Or I hear wrong?
Maybe I mentioned Lipschitz regularity, but it's just a modulus of continuity.
Is a modulus of continuity depending on the boundary data?
On the boundary data, yeah.
So the modulus of continuity is global in the world domain?
Yes.
Okay, and this is obtained through game theory.
Through game theory, yeah.
Okay, yeah, because let's say
Those are Pablo Blanc's results.
okay, so yeah, because basically what is missing the proof, let's say the echelon's proof, is that you do not have control of the gradient of the test function, basically, because of the degeneracy of the operator. And since neither you have Harnack inequality, you cannot perform a kind of iterative procedure to get C alpha estimate, something like that. So, but then, do you think that there's a kind of translation from the game procedure to a purely PDE proof? Can be translated?
I don't know.
Okay.
This I don't know.
Okay. Okay.
Well, probably the answer is yes, because for this stuff of reaching zero in finite time, we have to prove. The first one is the probabilistic proof, but the second one is a full PDE proof. And generally, I believe that when you have a stochastic interpretation of this and a stochastic proof of the result, a proof using probability, then you can use the intuition that gives the probability to construct sub and super solutions, or to construct barriers, or to construct things that gives you a PDE proof. But in the particular case of looking at regularity for lambda j equals to 0, I don't know. No sé. I don't know.
Okay. Okay. Gracias.
Okay. Yeah. Thank you, Julio, again. And Maria,